for the digital signal processing subject. The first is frequency domain analysis and fast Fourier transform. That is, it consists of data topics from sample theorem to mainly filter using the introduction to the ESP. ESP deals with representative analysis and manipulation of signals using digital systems like microprocessors or why digital is because of its high accuracy, community noise, flexibility, storage as well as transmission or latency, normally used in communication, on the go, audio, video, biomedical, and industrial systems. What is meant by Fourier transform, which converts time signal into frequency components. A DFT is nothing but discrete Fourier transform. The formula is x of k is equal to summation of n is equal to 0 to capital N minus 1 x of n e to the power of minus j by k n divided by capital. F of t is the fast Fourier transform, which is the efficient algorithm for computing the DFT. The types of filters: low pass filters, high pass, band pass, and band stop filters. The digital important digital filters are IAR and IFs. Applications of these. DSP is mainly applied in speech processing, normally for noise reduction and compression of signals, audio equalizers, ACG and filtering, image enhancement, radar and sonar signal processing, IoT sensor data processing, and power electronics signal monitoring. The tools normally used for the DSP is MATLAB, Simulink, Python, especially NumPy and SciPy, DSP processors, real-time application cards. What is meant by frequency domain analysis? Frequency domain analysis is the study of signals or systems with respect to frequency rather than time. Instead of observing how a signal varies over a time, we look at how much energy or amplitude the signal has at different frequencies. The variation between the time domain signal as well as the frequency domain signals are represented here. The magnitude response as well as the phase response of the audio signal is represented. The time versus frequency domain signals are represented. For example, this diagram represents the time domain and frequency domain views. Why frequency domain analysis? Many real-world signals are combination of sinusoids. In time domain, complex signals stay regular. Frequency domain, the same signals become easy to interpret, filter, and analyze. For example, speech, music, ECG, vibration, radar, all are analyzed using frequency domain analysis. What are the various tools used for frequency domain analysis? Fourier transform, discrete Fourier transform, as well as fast Fourier transform. This diagram represents the square waveform as well as its frequency spectrum of the square. Time domain to frequency domain. A single sine wave in time domain becomes a spike at its frequency to frequency domain. If x of t is equal to a sine 2 by f naught t, means spectrum contains two lines at plus f of and minus f. What are the parameters of frequency domain? Magnitude spectrum, phase spectrum, and power spectral density. Power spectral density is important in vibration, ECG, and communication. Some of the applications of frequency domain analysis are signal processing, communication systems, control systems, biomedical, mechanical, vibration. The comparison of time versus frequency domain analysis. We can compare with different features with representation, for best for tunes. The time domain is represented by amplitude versus time. Frequency domain is represented by sample versus frequency. Time domain is useful for waveform analysis. Frequency domain analysis is for filtering and spectral analysis. Time domain analysis is best for transients. Frequency domain analysis are best suitable for steady state components. The tools used for time domain analysis are time plots. Some of the tools used in frequency domain analysis are Fourier transform, discrete Fourier transform, FFT, and the PS. What is meant by sampling theorem? The sampling theorem states that a continuous time signal x of t can be perfectly reconstructed from its samples if the sampling frequency f of s is at least twice the highest frequency present in the signal. Sampling theorem is diagrammatically represented in this diagram. What is meant by Nyquist rate and Nyquist interval? Nyquist rate is Fs is equal to 2Fm, and oversampling means Fs greater than 2Fm, undersampling means Fs less than 2. What are the mathematical conditions for the sampling? If the highest frequency of the signal is max, the sampling frequency must satisfy Fs greater than or equal to F max. The minimum required sampling frequency is called the Nyquist rate, which is 2F max. The corresponding sampling interval is Ts is equal to 1 by Fs. Why sampling theorem is needed? To convert a continuous time, that is an analog signal, to discrete time signal. A sampling theorem is needed, as well as differential laws of information. The third point is in order to prevent aliasing, that is, in order to avoid frequency overlapping with signals. What is meant by aliasing? If the sampling frequency is too low, different frequencies appear as the same frequency. The reconstructed signal becomes distorted or imperfect. Phenomenon is called aliasing. Aliasing is a distortion that occurs when a signal is sampled at a rate lower than twice its highest frequency. Because of this, different frequency components become indistinguishable after sampling. High frequency signals appear as lower frequencies when sampled too slowly. The aliasing effect is represented as well. Aliasing occurs due to sampling with with respect to split. This diagram is also representing undersampling oversampling. What is the need of anti-aliasing filter? Before sampling, an analog low-pass filter is used to remove the frequencies above F max is equal to Fs by 2. This is called the anti-aliasing filter. Example, suppose the signal contains frequencies up to F max is equal to 3 Hz, Nyquist rate Fs is equal to 36 kHz. Common practical sampling rate used is Fs is equal to 8 kHz or higher. The concept of frequency in discrete time sequence. Discrete frequency omega is the radians per sample. Normalized frequency is cycles per sample. Valid digital frequency is minus 5 to 5 million per sample. Periodicity x is 1 million omega by 2 pi is ratio. Aliasing frequency set of Fs by 2 is over. Thank you.